Hi everybody, today we're going to talk about some division of polynomials. In this video we're going to look at polynomial long division, one of the techniques for dividing polynomials. In the second video we will look at the other technique called synthetic division. First we have to recall what it means to be a factor. A factor occurs when something divides into something else evenly. And in this particular case, I think we all understand that that word evenly has nothing really to do with even and odd numbers. What it really has to do with is the fact of meaning no remainder. Now, why am I bringing that up? Why, for division, looking at the no remainder case? Because if you would recall from some previous work, that the key to graphing polynomials is to be able to write the polynomials as factors so we can find their zeros to make their graph. And we reviewed several techniques for factoring those polynomials, but since not all polynomials can be factored so easily, sometimes we have to use some more algebraic and algorithmic sort of techniques like polynomial long division. We're going to be really concerned with the case about dividing in evenly, those factor cases. Now, just as a recall, just to show you numeric long division, because polynomial long division is based off it. Let's say I had some number 42,833, and we were going to divide that by 3. Now, whenever we do numeric long division, our goal is to try to get to see how many times the divisor will go into the first digit of the dividend. So we look at the 3, we look at the 4, how many times can 3 go into 4? We know it goes in once. Then we would take the 1 times the 3, get a 3, and we would subtract. We would subtract there 4 minus 3 is 1. Now that this remainder down below, this piece right here, is less than 3, we would have to continue and drop the 2 down there, get a 12. And no longer are we looking up here for the values that we want to consider to see how many times to go into 3. We're going to take our 3, and we're going to look, let's see if I can do this, at the 12 and say how many times does 3 go into 12. And 3 goes into 12 4 times. We put the 4. 4 times 3 is 12. And we remember that we subtract. And as we do this, our leading digits are going to disappear. And we're going to continue to work down and across from the largest digits to the smallest digits until we are done dividing. And so if I continue this out, we subtract, we get a 0. We need to drop the 8. 3, no longer we're looking at the 12. We're looking down here. How many times does 3 go into 8? And that's twice. We get a 6. We subtract. We get a 2. And I think I need a little more space here. Excuse me. 3 cannot go into 2. No longer are we looking at the 8. We're looking at the 2. So we need to bring down the, oops, I didn't bring it down far enough. We need to bring down the 3. That gives us a 23. 3 goes into 23 7 times, get a 21, subtract, we get a 2, bring down the other 3, 3 goes another 7, 21, subtract, we get a 2. And so at the end we have this result that we have a quotient of 14,277 and a remainder of 2. So that tells me that since it did not divide in evenly, we don't have a remainder of 0, that 3 is not a factor of 42,833. So that's one important thing we want to focus on here, whether we have a remainder of 0 or not, because that will tell us whether we have a factor. But we also want to look at this overall process of looking at the digits and working from the largest digits to the smallest digit, reducing down, and working our way across this way, getting columns to disappear so that we can work across. And as I have at the bottom of the screen here, this is the same big idea for when we work with polynomials. So take this in mind as we move to our first problem. What are the quotient and remainder? when this fifth degree polynomial is divided by x minus 3. So we're going to set it up much the same way, that I'm going to have my x minus 3, and I am going to divide x to the fifth plus 2x to the fourth minus 4x cubed plus 3x minus 18 by that x minus 3. And it's going to be the same idea, except in the last problem where I kept referring to digits, now I'm going to refer to terms. Terms are just a polynomial version of digits. So what I'm going to look at is I'm going to say, well, this x minus 3, how many times can I get x minus 3 into an x to the fifth? And really the big idea here is going to be, how can I eliminate that first column? And if I look at that, what I will use here is going to be a 1x to the fourth. Remember what we did previously? We would take the number that we put above, and I'm going to get a highlighter here, and we would multiply that by a divisor, x minus 3. So if I have x to the fourth times x minus 3, that's going to give me x to the fifth, x to the fifth minus 3x to the fourth. Now you'll be able to see here why I chose x to the fourth, because as previous with numbers, I'm going to subtract, but I'm going to put this in parentheses underneath. And now if I have x to the fifth minus x to the fifth, this subtraction of these two terms will give me a 0. And I don't really need to write that 0. And that first column will disappear. And once again, my work is going to come down and across like we wanted it to with our numeric example. So here, if I finish off this problem, x to the fourth times x is x to the fifth, x to the fourth times negative 3 is negative 3x to the fourth. And I subtract. X to the fifth minus x to the fifth is 0. 2x to the fourth minus negative x to the 3/4 is actually going to be 5x to the fourth. That's why I am very particular about using these parentheses, because when I subtract, I am going to need to distribute. Oh, that purple is not a good color there. I apologize. I guess we'll go with some blue here. That those parentheses are important because the subtraction I do needs to distribute through the multiple terms. And like we did before, so then we just continue. I'm going to drop down another term. I'm going to drop this term down, negative 4x cubed. And no longer is my focus going to be up here. Just like we had with the numeric example, now my focus is going to drop to here. And let's see if I can stretch this out a little bit. So my focus is going to be here. And it's almost like I can think about this ahead of time and say, when I subtract, I want to get a 0 there. So what is it that I need to put in this position? What is it that I need to multiply the x minus 3 by right here so that when I do this subtraction, I get a 0? And I'm thinking to myself, well, I've got an x right here. I need a 5x to the fourth. So up here, I'm going to need a 5x cubed and a positive 5x cubed. For when I take 5x cubed, multiply it by x minus 3, I will get 5x to the fourth minus 15x cubed. And now that I'll do the subtraction here. 5x to the fourth minus 5x to the fourth is 0. And then negative 4x cubed minus negative 15x cubed is going to be a positive 19x cubed. Once again, being careful with the subtraction, putting parentheses here helps me remember that the subtraction needs to distribute through the terms. I need to subtract those. I don't really need the 0 here. But once again, I'm seeing the columns disappear as I want them to disappear. Just like with our numeric example. I'm going to bring the next term down, 3x there. Now, what I notice here is, oh, I'm missing some stuff. That I go from a term of 4x cubed to a 3x, so I'm missing a term. There's no squared term in there. So what I really need to do is erase this, put in a 0x squared then plus 3x, and minus 18. In a numeric example, if you had zeros in the place there, you would just continue through. You would not have it gone. You'd have a 0 in its place. So I'm going to bring down this 0. So plus 0x squared. I'm going to put my parentheses and my negative in there. You don't have to do that, but it helps me think about it. And I'm going to think, what do I need here to get a 0 here? Well, obviously, 19x cubed minus 19x cubed. So then the question is, what do I put here so that when I multiply it by my divisor, x minus 3, I'll get that 19x cubed? Well, I think it's going to be a positive 19x squared, because 19x squared times x is 19x cubed, and then 19x squared times negative 3 is going to be negative 57x squared. I perform my subtraction, I get a positive 57x squared, and I continue the process. I'm going to drop down my 3x. I'm going to say to myself, what do I need to do to subtract so that I get a 0 in this position? What is it that I need? Excuse me. What is it that I need here so that when I multiply by x to the third and I do this subtraction, I get a 0? That's what I need. And that's going to be a plus 57x. So plus 57x times x would be 57x squared. And then 57 times negative 3, that's going to be a little big there. So it's 150 and another 21. So that's going to be a negative 171x. That number is getting a little on the big side. We'll see how it comes out. 57x squared minus 57x squared is 0. 3x minus 171x minus negative 171x is going to be plus 174x. And then I've got one last term to drop down, a minus 18. I don't need that 0. I'm going to change the way my screen looks so we can see the whole thing here. And I do the same thing. I'm going to want to subtract so that I get a 0, and I've got a positive 174x there. So it's going to be plus 174. When I multiply, I'll have 174x. Now 174 times 3, 300, another 210, 510, 522. I did that in my head, and I maybe should have gotten a calculator, so I hope I'm right. So that will give me 0. And then negative 18 plus 522 will give me plus 504. Right. So at the end of this, if I look at my previous example, the value that was over my division symbol I called the quotient, and the value that was left over I called the remainder. So I've got that right there. So I would say here that I have a quotient of x to the fourth plus 5x cubed plus 19x squared plus 57x plus 174, and a remainder of 504. Yeah, it's a bit of a long process, but sometimes that's all you've got, and I just wanted to demonstrate one problem for you so you could have something to come back and look at, and we'll talk about some more of the details when we get to class. Thank you.